Everybody. Hopefully, after going through all of the ionic bonding stuff, things are pretty clear to you about what happens when a metal and a nonmetal stick together. Today, what we're going to be talking about is covalent bonding and everybody's favorite, the Lewis structure drawings that go with the covalent bonded things. So if you remember from last time, we talked about electronegativity values being how much an element is able to pull electrons towards itself when it's in a bond with another element. And the bigger the difference in the electronegativity value, the more the element is able to pull those electrons. And we talked with ionic bonding about how if there's a big enough difference in electronegativity, you end up with a situation where you have the electron actually physically leave, usually your metal, and go to your non-metal, and then you have the two ions that attract to each other. But I would say that a lot of times there is not a big enough difference in the electronegativity values between the two elements in a bond. And so instead of a transfer of electrons happening, there is a sharing of electrons that happens. And that's what we call a covalent bond. So again, there are two types of covalent bonds. There are nonpolar and polar covalent bonds, and we will get into that difference in another lecture. But right now, we're just talking about anything basically that has a small enough electronegativity difference where the two elements are sharing electrons instead of one transferring. So in a covalent bond forms when two elements end up sharing electrons, and specifically they share their valence electrons, that kind of outermost shell, in a way that helps them satisfy the octet rule without actually losing any electrons or gaining any electrons. So when you think about a covalent bond, what I think about a covalent bond is it's a handshake between two elements. And when those two elements make the handshake, they end up sharing electrons, and those electrons count towards the total number of electrons for both atoms, and that's the reason why they join together in the first place. So they are trying to achieve that full 8 in their outside shell for stability like a noble gas has, but instead of transferring an electron, they share an electron instead. Covalent bonds most often form with nonmetals and nonmetals together. So we see this happening with things on our periodic table in that upper right-hand corner that we see kind of above the stairs. What ends up happening is when you have covalent bonds, you can create up to 3 bonds between 2 atoms. So if I have one atom here and one atom here, I can share up to 3 pairs of electrons with them. There is some research that suggests that carbon can produce what we call a quadruple bond, but it's not anything that you guys are going to ever encounter. So as far as we're concerned, the most you'll ever see is 6 electrons total shared, or 3 pairs. When we talk about electrons, we talk about them being pairs of electrons because there's always 2 kind of that are shared. So in the case of this picture, this overlapped pair here is what we call our bonded pair of electrons. And then if you consider in this left atom here, a pair, and a pair, the ones that are unbonded, we call unshared pairs or lone pairs because they aren't bonded with anything. Now, we've talked about oxidation numbers a little bit and how oxidation numbers are pretty predictable based on where your elements are on the periodic table. But as soon as we kind of start to bond nonmetals and nonmetals together, oxidation numbers kind of go out the window. And so I'll kind of show you as I go through some examples what happens, but nonmetals have really dynamic oxidation numbers depending on what they're put together with, because sometimes things that we assume are all going to be negative have to be positive to end up kind of making things work out. Now, ionic compounds are kind of drawn in one specific way, and we're going to go through one example of those as we get to the examples in these problems. But when we draw covalent compounds, we draw what's called a Lewis structure or a Lewis dot structure. And a Lewis dot structure is a 2D representation of a way that we predict how the elements are connected together with bonding pairs and unshared pairs of electrons. There is data that goes to support the more correct potential Lewis structures. And as we start to get molecules that are big, we can see multiple Lewis structures for a given chemical compound. But we'll kind of get into that stuff a little bit later. Right now, we're just going to kind of brush the dust off your drawing skills and show you some things that we did not mention to you in chemistry. So when you draw a Lewis structure, the first and most important thing is that you need to add up the total number of valence electrons in the compound. So you're going to use your families on the periodic table to figure out the number of valence electrons in there. It's really important that you do this. Your picture can have no more or no less than those number of valence electrons. So it has to have all of them in there, and you can't have anything more or less than what your total is. If you skip this step, you're in trouble. Okay? Then you are going to draw a skeleton structure for your compound. A skeleton structure is like a first draft for your element. It's, you can screw them up and redraw them. It's up to you, but it's the first round of your drawing. When you draw a skeleton structure for a Lewis structure, usually the central atom is written first in your chemical formula, but there are some exceptions to that, and that's usually when hydrogen is written first. So hydrogen usually is not a good central atom, but pretty much anything else can be. In the past, we've said trying not to put halogens in the middle. That's not always true, so we'll talk about that in a little bit. What happens then is you usually pick one atom if the central atom is written first, and the others distribute around that. If you see that your formula is written with two first things, like your formula is C2H something, what happens then is you may get a Lewis structure that starts to branch, and you might have 2, 3, 4, 5 central atoms, and we'll get into those as we get a little bit more complicated. H, like I said, never going to be in the middle. Hydrogens only ever form one bond, so they're not particularly good centers. Elements are never going to make more than 4 bonds if they're in the first or second row of your periodic table. So period 1 and period 2, those elements are only ever going to make 4 bonds. Otherwise, things get a little wild, and we'll talk about those in just a minute. Okay. Boron is okay with 6 electrons, not 8, because of the way that boron is structured. If you draw a Lewis structure with boron, understand that boron is okay with 6 electrons, not 8, and that will be helpful later on. Okay, so then after you draw your Lewis structure and you get your skeleton structure set up, for every bond that you draw in, you're going to connect those skeleton structures with a bond. For every bond that you draw into your structure, you are going to subtract 2 electrons from your original valence total. And it's really important that you don't forget to do this, because otherwise your numbers are going to be screwed up. Then you are going to distribute the remaining electrons around your outer elements to satisfy the octet rule. It is possible that you might run out of electrons, especially on the center atom. So when you draw a Lewis structure, you are going to fill in the dots around the outer atoms first, and then you move to the central atom, okay? If you run short, we'll deal with that. Okay, if you are short electrons, what you need to do is you are going to take those and move the electrons from outer atoms that you satisfied the octet for and slide them into the middle to create either a double bond or a triple bond. It depends on what is going on with your particular atom. You may need to only end up sharing 1 extra pair of electrons, but you might need to end up sharing 2 and create a triple bond. Okay? This is something new compared to when we taught you in regular chemistry. If you have extra electrons, they go on the central atom if the elements are in period 3 or down. So elements that are in period 3 or down have the availability to have electrons sitting in a D shell. If you remember our electron configuration, you get into the 3rd energy level and you have D shells all of a sudden. So what can happen is sometimes elements will actually have extra electrons in their Lewis structure. And if there's extra electrons, those can get stashed in the D shell, kind of like a little junk drawer where your electrons go. And so if you have extra electrons, they go on the central atom if you're in elements, if you are in elements with rows 3 and down. It is possible also, like I said, to create more than 4 bonds if you're in the 3rd period or lower. So if you start to see elements that have 5 things attached to them, 6 things attached to them, that is possible if we are dealing with elements that are in your 3rd period or lower, which we call an expanded octet. So what I'm going to do is I'm going to give you guys 6 different examples that I'm going to go over in the 2 following videos to show you how to do these. If you want to give them a try, go ahead. Don't be shocked if some of them are wrong, because there's some new things that you probably haven't seen. And we'll go through those examples. So example number 1 that I'll be going through is lithium chloride, LiCl. That's an ionic compound. So I'm going to talk about how they're going to ask you to represent an ionic compound. We're going to do NF3, NO3 minus, and then in the second video, I'm going to do PF5, ICl4 minus 1, and NO. My guess is you will probably have an easier time with 1 through 3 versus 4 through 6. So if you find yourself struggling and you feel good about 1 through 3, that's great. The new stuff's probably going to be coming in 4 through 6. So hold tight, get ready to do some examples, and then come on around to the example videos and we will be done with them momentarily.